Aloha nui kako. Welcome to another edition of Live from NOIRLab at Hawaii. My name is Alyssa Leinani Lozi, and I'm your host for today's show. Our moderator is Jamaica Marshall. She'll be taking all of your questions from the YouTube chat and reading them aloud for our special guest astronomer, Siyi to answer. Any questions you might have about the presentation and about astronomy in general, we are happy to hear them. So before we get started, I do want to talk a little bit about the Gemini North telescope. And so Gemini North is the telescope pictured here. It is located near the summit of Mauna Kea on Hawaii Island, and it is the telescope that we, all three of us, work for. So we are all very lucky to be working at the International Gemini Observatory, a program of NSF's NOIRLab. Now, Gemini North is located here in Hawaii, but Gemini South is an identical twin telescope located on the summit of Cerro Pachón in Chile. This way, we have two telescopes in both hemispheres of our planet, and we can see the entire night sky around our globe. Gemini is funded by a multitude of international participants. So we receive funding from the United States, Canada, Chile, Brazil, Argentina, and Korea. And for our science highlight for this week, I just wanted to mention our newest photo release of the Carina Nebula, pictured here. And it's a really great picture, as you can see, especially this particular graphic, because at the top part, we can see this image when used with adaptive optics, specifically the Gemini South Adaptive Optics Imager, GSAOI. And the bottom image shows when we take this same image with the same telescope, same filters, but no adaptive optics. And so the clarity that we are able to achieve with such a large telescope and the combination of adaptive optics is really quite unprecedented. So this is a great image for you to go and check out at the link in our slide here. We will also include the link in the description of the video when we repost this later. And you might also notice that there are a lot of little stars in this image. Some of these might even be baby stars, which is very appropriate sort of to talk about when we get into our white dwarf topic with Siyi. White dwarfs are a much older stage of the star life cycle. And here in this nebula, we can see the sort of beginning stage, the baby stars. This is a star-forming region, and our telescope, which specializes in infrared observations and has these wonderful adaptive optics to get really clear images, can not only take really beautiful photos, but is able to study these stars in their early infancy, if you will. And with that, I'm going to let our guest talk about her presentation now. As a little introduction, Siyi is from China and got her bachelor's degree in Nanjing University, followed by a PhD in astronomy from the University of California, Los Angeles in 2014. After that, she worked as a science fellow for the European Southern Observatory in Germany, and Siyi joined us here at Gemini North in 2017. All right, take it away, Siyi.
Thank you, Alyssa. I think you need to stop sharing your screen, Alyssa, so I can do mine. Great. Okay, hope this works. All right, hi everyone. My name is Siyi, and as Alyssa has said, I'm currently an astronomer based at the Gemini Observatory, which is a program under NSF's NOIRLab. Very glad to be here and to have the opportunity to discuss my research topic with you. My understanding is you are welcome to ask any questions. I'll try my best to answer them. So the topic today is the solar system in 6 billion years. So 6 billion, how long is 6 billion? I would just want to spell it out. It's 6 0 0 0 0 0 0 0.000 years. So it's a very long time. How long can we live as a human? 100 years at most. So one fascinating thing about astronomy to me is even though as short-lived as we are, we can try to understand the universe, which is so big and so large, so old, and sometimes we can make sense of them. That's really why I want to do astronomy. So before getting started, I just want to say a little bit about myself or my telescope journey. And as Alyssa has said, I got my undergrad degree in Nanjing University. So this is actually the first ever observatory I've ever used. Yeah, so you can see the dome. The dome on the left-hand side is our little telescope. So that's what I did for my undergraduate study. Somehow, ever since then, I just love doing observation. I like to be able to use a telescope, observe part of the sky that nobody else has ever done before, and try to see if I can understand what I'm looking at. So after my undergrad degree, I went to UCLA to do my PhD. This is actually at the UCLA remote control room with my PhD advisor, Mike Jura. So there we were controlling telescope from Mauna Kea, actually Keck Observatory, because the University of California is a partnership with Keck. So I actually used Keck quite a lot for my PhD studies. Interestingly, I've never traveled to Hawaii during all these years. I mean, I've never traveled to Hawaii for observing. I've traveled here for fun, but not really for my observing because the remote observing room was set up so nicely. And then during my PhD, I also used a few space telescopes. One is the Hubble Space Telescope. So this is an image of Hubble. It's in low Earth orbit, which means this telescope is orbiting around the Earth. Specifically, I use the ultraviolet capability of Hubble. We can't really do it from the ground because our atmosphere absorbs most of the UV light. So we can't really do that. And I use Hubble for that. I also used another space telescope called the Spitzer Space Telescope. It's a bit further away from us than Hubble. It's in a place called L2. And it's specialized in observing things in the infrared. So that's another mid-infrared or long infrared. That's another wavelength that's blocked by our atmosphere. And then after that, I worked at another observatory called the European Southern Observatory. And they actually are in charge of several observatories in Chile. So this is a photo that I took at the Paranal Observatory. And the telescopes are called very large telescopes. So astronomers are great with names. So there are 4 8-meter telescopes, and you can kind of see them here. And then each of them is called Unit Telescope 1, Unit Telescope 2, Unit Telescope 3, Unit Telescope 4. And then you might also notice there are some smaller domes there too. There are also 4 1-meter ancillary telescopes. So they can either work together or work separately. And then this is one picture, me with a colleague. We're taking a break. So we're looking at the stars and also shooting with a laser. And I've been with Gemini since 2017. So in this presentation, I will give you a brief overview about what I do. And actually, we'll talk about research with all these telescopes. Well, I guess not the one with Nanjing University. So I see, Alyssa, you have a question?
Yeah, so thanks so much for including this little bit of background, your telescope journey. I love that. Would you have any advice for young astronomers or someone who's just starting undergrad and how they could eventually become an astronomer at an observatory like you?
Sure. Okay. So the question is if I have any advice for young career future colleagues. I think it's very important to keep your curiosity and keep interested. It's always good to know what you want and what makes you happy. I think that's really the most important thing. If you're curious about something, I think that's the best motivation to keep you going. All right, so I'll move on to the main science topic. So this is the life cycle of the sun, and it's a sun-like stars. They all have similar life cycles. So basically, they are born out of a molecular cloud. The cloud collapses, and then it forms into stars are born. Our sun has pretty much evolved peacefully for about 4.5 billion years. That's the current age of the sun, the solar system. And this is kind of how it looks like. The current view of the solar system, we have the sun in the middle, we have terrestrial planets, like Venus, Mercury, Earth, and Mars. And then there are the asteroid belt, which is really like the leftover material of planet formation. And then beyond the asteroid belt, there's an ice giant and a gas giant like Jupiter, Saturn, Uranus, and Neptune. And beyond that, there's also more minor planets. We call it comets or Kuiper belt object. So we think it's extrasolar planetary systems also have very similar configurations. For the solar system, it probably will stay more or less quietly for quite some time. This is now for another 6 billion years. It will stay the same. The sun right now have active nuclear reaction going on. That's what gives it heat. But then in about 6 billion years, it will use up all its fuel. So it can no longer maintain this nuclear reaction. So what happens first, it will collapse. And then afterwards, it will expand. It will expand very big and then become a red giant star. And eventually, a lot of material will get expelled out, basically leaving from the sun. And then that will form a phase called planetary nebula. Planetary nebula like create very pretty images in the universe. So this is one of my favorite, which is called cat eye nebula. So if you look like a cat's eye. And then after all this material is gone, what's left behind is a white dwarf. So this is the end stage of all this. So if we want to know what will happen to the solar system in 6 billion years, we can either wait 6 billion years and see what happens, or we can just look at what happens around the white dwarfs. So that's the topic of this presentation. Oh, yeah, sorry. So this is a famous picture of the white dwarf. So it's actually taken by the Hubble Space Telescope. It's actually the Sirius system. Sirius is a bright star you can see at night. And so this is Sirius A, while here, this is the white dwarf component. It's Sirius B. So the bright star at night is actually a binary star system. So this is one of the most famous white dwarf. Okay, so before getting started, let's talk about some fun facts about white dwarfs. So most of the stars in the Milky Way will become a white dwarf. Like this is a very common end stage. And white dwarf is actually highly compressed. This is a kind of a comparison. They have about half of the mass of the sun, but the size is very comparable to Earth. So this is the relative size of the white dwarf. This is the size of the Earth. So it has very high gravity. The gravity is about 350,000 times of Earth's gravity. So basically a teaspoon of white dwarf matter weighs about 5.5 tons. To just give you an idea. And some of them can become supernova, a very energetic event in the universe. Luckily, our sun will not become a supernova, so we're good to that. So the specific question here I want to answer is, what happens to planets around the white dwarfs? Are they still there, or are they completely gone? So here's an animation made by ESO, which kind of shows a fate of one planet when the sun evolved off the main sequence. So you can see the yellow thing is the central star. It's expanding right now because it's turning into a red giant. And then here is basically a planet, an unfortunate planet. You will see what happens. So in this specific case, the planet was orbiting too close to the sun. Eventually it will get swallowed and then probably won't survive the process. So unlucky planet. So actually for a very long time, people thought white dwarfs are dead stars because so many crazy things happen. There probably is nothing left behind. But nature never fails to surprise us. And that's what I will be talking about. So first talk about a discovery first made by NASA's Kepler mission. The mission was launched in 2009. The main goal is actually to search for planets or Earth-like planets around the sun-like stars. And they use a method called transit. So I'll show you a video about what that means. So here, I'm just trying to say, so this is basically the star. And you can see here the planets. And then when the planet moves in front of the star, if you measure the brightness of the star, you can see it will become a little bit dimmer. And then if it's a larger planet, it becomes even the flux drops even more. I'll show it again. So this is called the transit method. It's a very successful method, and it have discovered thousands of planets outside the solar system. So it basically, when the planet move in front of the star, the total brightness of the star would decrease. So that's a basic idea. And then Kepler made a surprising discovery. So this is a white dwarf. It's called WD 1145 plus 017. WD is white dwarf. And the following is just its coordinate. And it was discovered by my collaborator, Andrew Vandenberg. So here I'm just showing the light curve of this object. So for one thing, this white dwarf actually have six different objects transiting in front of the white dwarf. So I'm showing the period here. They are all between 4.5 to 5.0 hours. So they are all very, very close to the white dwarf. And another thing is you can see the shape looks a bit weird, right? They don't quite look like the symmetric shape that we were looking at the animation. It seemed like there was something else going on. So we did some follow-up studies. This is the result from a follow-up study, similar plot as before. This is the relative brightness. This is time. The black dots are our data. And the red line are two models. So if the transiting object is a solid body, and it will look more like the red line, which have a very symmetric profile. However, here we are seeing something very asymmetric. It looks more like it's some solid body with something else. It's more, we think it's a dust cloud, so it's creating this huge shape. And then this immediately got a lot of interest after its first discovery, because we are really trying to figure out what's going on. So this is one set of observations. So time goes from bottom to up. So it's basically from November 2015 all the way until July 2016. And each light curve is separated by about a month. And then they are all shown in the same way. So you can see the light curve actually looks very different, right? In November, there's so many dips and things going on. It's very hard for you to find a flat point. While if you go to July, there's only this one dip here, while everywhere else, it seems pretty flat. So I don't think we've seen anything like this before. Somehow this system is actively changing, and it's changing on monthly, actually daily time scale. So what's really going on? I just want to say this data set is actually obtained by a collaborator, Bruce Gary, and this is his observatory, Hereford, Arizona Observatory. So Bruce used to work at JPL, and he retired. And then I remember talking to him. He says after his retirement, his goal is to become an amateur astronomer. So he looked at the map of the US, and he said he had 10 criteria about where he wanted to retire to. Top one is a place with a beautiful night sky. And he found a good location. And he had a small 14-inch telescope there, but it produced really beautiful light curve, for all my observatory, all my research projects. I'm really grateful that he's doing this, and he's still continuing monitoring it. All right, so what's really going on there, right? What are the things can really cause something to change on such a short-term timescale? Our best hypothesis, we think, is we are seeing an asteroid in the process of disintegrating. So the asteroid somehow got very close to the white dwarf. It's in an orbit about every 4.5 hours. And then we are seeing huge fragment dust cloud coming off the white dwarf. That's why these things are producing such huge variable transit features. All right, I see a question from Alyssa.
Yeah, so thank you for sharing with us about Bruce Gary, because that's amazing. What a retired person is giving you amazing light curves to then go and look for exoplanets with. Yeah, okay, so I guess my follow-up question for that then would be, obviously there's a limitation to what someone like Bruce Gary could do, so how much further can you get in depth with these observations, say on the Gemini telescope?
Right, so that's a really good question. I will start with, I really appreciate all the effort from amateur astronomers to help study this object, because it's amazing, right? So what Bruce has been doing for us particularly useful is he can monitor this object night after night, right? And really trying to figure out what's going on. If he finds there's a very strange, bizarre event, I mean, particularly in this object, we don't really know, we can't really predict. So if he observes something really unexpected, he will let us know, and it will be like, oh, we really, now is the time to follow up with the large 8-meter, 10-meter telescope, trying to figure out what's going on with the system. So I think it's a really nice collaborative effort we have here. All right, then I will tell you my most ambitious project, observing project I've ever done. Because this system is so variable, we really need all the best facilities, really, try to understand what's going on. So we managed to get time on the Hubble Space Telescope, the Spitzer Space Telescope, and the 3 of the very large telescopes, all observing at this system at the same time. And it happened on March 29th, 2016. I'll always remember that day. And then I'll just show you what we see. I know it's probably not as impressive, but it's the most beautiful light curve I've ever seen. So I'll walk you through what we are seeing here. So here I'm showing the light curve from top to bottom. So first is from the Hubble Space Telescope. Then it's from WET, actually, it's Whole Earth Telescope. Oh, sorry, missing it here. And then there's this is an optical light curve. Then there's a K-band, so it's an infrared 2.2 micron light curve from the very large telescope. And then there's another light curve from the Spitzer Space Telescope. This whole thing lasts about 6 hours. And I'll walk through some of the features with you before explaining what we got out of it. So first, Hubble Space Telescope. You can see those gaps, right? In between them, you might wonder what happens. So the reason is because Hubble is in orbit around Earth. So let's say, how to say? Okay, so this is the Earth, this is your target, and then let's say Hubble is orbiting around this, right? So Hubble can only observe your target when Earth is not in the way. When the Earth becomes in between the Hubble Space Telescope and your target, you cannot observe that target, right? So these are why like Hubble's orbital period is about 90 minutes, but you can only observe your target about half of the time. So at first, you might see this is a very unlucky encounter. There's a big transit here, which was missed by Hubble. There's another big transit here, which was missed by Hubble. But luckily, I still got some part of here and here that will allow me to do the analysis. Now I'll move on, talk about the optical part. I was hoping to do something with a very large telescope, but I was making it too fancy and didn't work. So I almost did not have an optical light curve. Then another collaborator, totally we were not coordinating, they got an optical light curve. So luckily we have a simultaneous coverage. And you can see there's this very big deep transit happening around here. And there's another one around here. And then I'll go to the VLT. So on that night, I was actually in the observatory. I was there like ready to use all 3 telescopes, right? And then during sunset, the weather was actually very clear. I didn't see any cloud and everything looks great. So I'm like, yay, okay. Because I have my timing window starts at about 10 p.m. until 3 a.m. But then somehow at the end of twilight, basically a lot of dark clouds came. Like basically we cannot see anything. We could barely see the moon. And I was like, ah, oh, great. So all the telescopes were closed. The humidity is 100%. And I was like, ah, so maybe it wouldn't work, right? And I was kind of stressed and started watching movies. Then 8 p.m., 9 p.m., 10 p.m. And somehow at 11:30 p.m., all the local time, all the clouds just disappeared. I'm like, oh, yay, great. So they actually opened the telescope. So I didn't quite get all the time I was asking for, but I still managed to get a really nice transit with the very large telescope. And then this is Spitzer. So I was like, thank God I have time with the space telescope. There's no weather, right? That will always be good. So we also get a very nice light curve at the 4.5 micron. All right, so that's the story behind all these data. So what do we see? So if you look at them carefully, because they are all simultaneous, right? You do see the same transit happening in all these light curves, but the transit depth is actually very different. And it's deepest in the optical, it goes to about 50%, while in K-band, it only goes to like 35%. And in the Spitzer band, it's even much shallower, right? You can barely see it, maybe like 15%. So with that, a bunch of modeling, a bunch of math, what we figure out is actually the dust grains must be very large. So not a lot of small dust grains. We can put on a minimum size, about 1.5 micron. So that's what we can say about the feature of the transiting material. And we also learned a lot of other interesting things. One thing is this white dwarf actually have a dust disk. So this is some kind of plot astronomers like to make. So the main thing is basically you look at the flux of this system as a function of wavelengths. So the x-axis here is wavelength, y-axis is flux, and the black line is a typical model for this white dwarf about how it's supposed to look like. And then the red symbols are our measurement. So you can see in this part, the optical part, they agree pretty well. But when you go to the K-band, which is infrared, and even longer wavelengths, the measured flux is much higher than what it should be for just a single white dwarf. So we think the best idea is this white dwarf actually have a dust disk. And we can somewhat constrain the size, the temperature, and we think it's similar to Saturn's ring. So just for comparison, so you see white dwarf is here. White dwarf has a similar size as the Earth, and then it has this big debris disk around it. The size of the disk is pretty close to Saturn's ring. So yeah, so it's pretty interesting that this white dwarf also have a dust disk. Then we look at it even a bit further. I got data from the high resolution spectrograph on the Keck telescope on top of Mauna Kea. This is a high resolution spectrograph, so you can disperse the light a lot. And then that will allow you to study basically the chemical composition, like what is really in the atmosphere of the white dwarf. So here I'm showing a small part of the wavelengths, a very small part, and this is flux. The black line is the data, and the red line is the model. So you see, we detected a lot of heavy elements. We detect a lot of rocky material actually floating in the atmosphere of this white dwarf. So we see like chromium, titanium, iron. We actually see a lot of things. So this white dwarf is very unique because not only it has this debris around it, it also has rocky material floating in its atmosphere. And when we do a more detailed abundance analysis, we can figure out what kind of material is it. So here's a showing as the mass fraction, a pie chart diagram. So more than half of it is oxygen. Then it also has magnesium, silicon, iron, and then a few other minor elements. And then we can compare that to the composition of bulk Earth. So this is how Earth looks like. So to first order, they look pretty similar. So basically the dominant elements are always oxygen, iron, silicon, magnesium, right? It's just a rock there seems to be similar to a rock here. But then you can also see this rocky material have a lot more oxygen than Earth. So we think one explanation is probably this material have water or have ice in it, H2O. That's why it makes this system so oxygen rich. All right, I see Alyssa had a question.
This is such a cool discovery to talk about, Siyi. I just wanted to, I think, highlight a couple of things from what you said that were just really amazing and to help sort of summarize for our audience. So in your very first slide, talking about this white dwarf, I love that you explained the light curves and all those different, what they meant. But I just wanted to summarize for some of our viewers that all of these light curves, as Siyi said, were taken simultaneously by different telescopes, all looking at the same object. So that's really cool. And so astronomy is very, very collaborative. But I think to help some of our viewers, especially non-astronomers, understand the process of astronomy. So one, it's very, very collaborative. It probably took you a lot of logistical work to get all of that time on those telescopes at the same time. And then also from your observation night to actually processing that data and figuring out what you were looking at, about how long did that take?
Oh, I guess you can see, right? We got the data on March 29th, 2016. The paper was published in 2018 and 2019. So a few years.
That's awesome. No, I think it's often overlooked that science does take a very long time, right? So. 2 years is not that bad though.
Thank you. I try, yeah. And Jamaica, you have a question too?
Yes, fantastic presentation. And so we have a question and some comments, but I'll start with a question. This is from Leonardo Paredes. And Leonardo says, besides the infrared excess, is it possible to detect the disk's presence on the actual light curves themselves?
So the question is, apart from the infrared excess, is it possible to detect the disk itself from the light curve? That's a very good question. So in fact, if you look at the Spitzer light, short answer is yes, we can. The way to do it, well, it's because the Spitzer light curve is basically many of the photometry point, right? It's basically many of the infrared excess. So in a way, yes, when you look at the Spitzer light curve, you are basically looking at the infrared excess for however long it is. The interesting thing really for me is in this light curve, the only infrared variability we've seen is caused by this transiting material, like basically kind of here and here. We did not see any other variability. I thought that's interesting or even unexpected, because if there's an asteroid there actively disintegrating, interacting with the disk itself must also be changing, right? But somehow we didn't really see it. The disk seems very stable. So hope that answers the question.
Thank you. No, that was a great explanation. And if you have a follow-up question, Leonardo, please go ahead and leave it in the chat. And I will say that to everyone in our YouTube audience, thank you so much for joining us. And please feel free at any time throughout our presentation to leave your comments and questions in the chat.
Thank you. All right, so I'll move on. We talk about the dust disk. We talk about it have rocky material floating in the atmosphere. And then we've studied this system a lot, right? A lot, just to summarize. So we think this is a white dwarf, and it have an asteroid disintegrating, actively transiting around it, right? Causing all these crazy things with the light curve. It have infrared excess from a dust disk. The white dwarfs itself also are accreting material. So it have material, rocky material floating in the atmosphere. So we've learned a lot, but we still have a lot of open questions. So first one, really, how did the asteroid get there? So I want to say, despite the first discovery in 2015, we have been searching. I think now we find one other system look more or less like this, but we haven't really found anything else. So it must be very rare, right? So how did the asteroid get there in the first place, really? So our idea is it probably experienced some kind of gravitational force from a third object, either a planet or a passing by star. And basically, this unlucky asteroid got kicked, into so close to the white dwarf, and that's how we see it. And the second question is really, what will happen next? Right? It's not a nice place to be, and it's not a stable state. It cannot last forever. How long, like when would this whole asteroid become disintegrated? We don't really know. We have to keep looking. From our best estimate, this kind of tidal disruption lasts about 1,000 years to maybe 10,000 years. So it probably will still be ongoing in my lifetime. And also, I just want to say, this system is about 180 parsec away. So it's about 700 light years away. So it takes light about 700 years to arrive to us. So what we are seeing happening right now is really what happened 700 years ago. So right now, maybe this asteroid has already completely disintegrated. We just won't know for another 700 years. Last bit, really, how often do we see this? We need to keep looking, right? In order to see, really to understand how often we see this. All right, that brings me to the next mission. So Kepler ended in 2018, retired in 2018. And then NASA launched a new mission called Transiting Exoplanet Survey Telescope, also in 2018. It's called TESS. So the idea is very similar idea to Kepler, also looking for exoplanet using the transit method. And the difference is really the survey strategy. TESS is an all-sky survey. So it will look over the entire sky, basically searching for planets, transiting stars. So TESS started out looking at the southern hemisphere. So this is a panorama of the southern hemisphere. You can see very beautiful Milky Way here. And then in the middle, it's the Large Magellanic Cloud. So this is a TESS survey strategy. And then just in comparison, this is Kepler. It's not to scale. So Kepler's field of view is actually much, much smaller. So Kepler is looking at a very small part of the sky, and then they stare at it for years. So the goal is really to search for Earth-like planets. So the orbital period would be like 1 year, right? While TESS and each field, TESS only stay there for about 30 days. So that's kind of a different survey strategy. And then again, we find something kind of unexpected. We find the transits around another white dwarf. This is WD 1856, again, identified by the same collaborator. So here, I'm just showing different optical light curves obtained from different telescopes. So first, this is from TESS, and then we followed up with all kinds of different telescopes. To start with, you can see this looks more like a normal transit, almost a bit boring, right? Compared to 1145. This is very stable. We've looked at it many times. It always shows like this. And then from the light curve, we can back out its size. And we find it's actually a Jupiter-sized object orbiting around this white dwarf. And the period is about 1.4 days. So it's very stable. That's why there is an artist illustration. So just want to say, this is a white dwarf. The white dwarf is about the size of the Earth, right? And the planet is Jupiter-sized. So the planet is actually much larger than the white dwarf. So if they are completely aligned, we will be able to see total eclipse, which means the white dwarf will completely disappear behind of the Jupiter. The transit depth would go to 0. But in this case, because the system is not completely edge-on, so when the planet moves in front of the white dwarf, it doesn't completely block the white dwarf. It only blocks about 60% of the light. So that's why we still see a little bit of light from the white dwarf. And with that, we can constrain its size. Okay, so I see there's a question from Jamaica.
Yes, thank you. Fascinating, definitely. And you're getting a lot of comments here, and definitely, I'm sure, getting us to think about these light curves and what we can learn from these light curves. So in thinking about the discoveries and breakthroughs in your research, we have a question from Chance, our former intern, Chance, at Gemini. And Chance, we're so glad to have you. And of course, welcome to all NOIRLab colleagues who are in the chat with us today. We definitely appreciate your support and participation. Okay, so Chance says, have you applied any discoveries or breakthroughs in understanding the physics of accretion disks in other stellar phenomena to how they actually relate to accretion disks in solar systems?
Okay, so the question, just making sure I understand the question. So the question is basically, have I ever applied the physics we learned from accretion disks in other systems to the white dwarf system or to the solar system?
To the solar system. And I also just dropped the question in the chat.
Sure. Okay. So I would say in general, like accretion disk is a pretty well-known phenomenon, right? We've seen it in many other systems too, not just around the white dwarfs. Say we've seen it in like main sequence stars have debris disks. We have protoplanetary disks. We even have accretion disks around the black holes or even AGNs. So more or less, they are governed by the same kind of physics. So like the energy level will be different. So like the detailed structure will be a bit different. But then in the solar system, I guess I'm not quite sure like what specific type of accretion physics is involved in the solar system. We did try to draw an analogy between the white dwarf and disk and the Saturn's ring. So we think the evolution scenario is actually pretty similar. So we try to use Saturn's ring kind of as a starting model to help us understand like how would the white dwarf disk evolve.
Excellent. I'm pretty sure that that was a good answer, response to his question. And you know what? He also has a comment, if I may. He continues on, Chance continues on saying, having done AGN research, and for our audience, AGN stands for active galactic nuclei. So having done AGN research and now X-ray binary system, Chance says that his professor has been emphasizing the importance of accretion disks across many fields.
Yeah, that I completely agree. Maybe Chance can help me model these systems and really understand what's going on. That would be awesome.
All right, thank you.
Sure. All right, and I'll move on. So I just want to summarize from the light curve, what we've seen is there's a Jupiter-sized object orbiting this white dwarf every 1.4 days, right? So then our next question really is it really a planet? Because for Jupiter-sized object, so this is just a size comparison, it can go from low mass stars to brown dwarfs or to Jupiter, right? So it might not necessarily be a planet. It could just be a boring, not so boring, brown dwarf or a low mass star. So we really need to measure its mass in order to be sure this is a planet and not other stuff. And then, so typically when people do exoplanet research, they determine the mass from the radial velocity study. So here's an animation. I'll show you. Hope it works. Yeah. So you can see as the planet move around the star, and if you look at the spectrum line of the star, you will see it move around, shifting back and forth. The reason, okay, I'll just play it again. The reason is because the star is not standing still. The star is also moving around relative to the center of its mass, right? So depending on how much the wavelength shift around, we will be able to constrain the mass of the planet. So we're like, okay, sweet. We should just take a spectrum of the white dwarf and then see how much it shift. Then we'll figure out how, like if it's a planet, what's the mass of the planet. Unfortunately, nature doesn't work that way. It turned out this white dwarf have no spectral lines. So we've observed it with many different telescopes, you see, including Gemini, Genus, which provides this long infrared part of the spectrum. So we did not find any feature from the white dwarf's atmosphere. Yeah, so this white dwarf is called a DC white dwarf. C stands for continuum. So this white dwarf only have continuum, have no spectral line. Like, fine. Okay, so we cannot figure out the mass this way. There are other ways to figure out the mass, not as conventional. So here we ask help from this retired telescope, Spitzer Space Telescope. We try to measure the mass from the light curve. So here is basically a comparison. And on the left-hand side is an optical light curve we got from the GTC telescope. And on the right-hand side is the light curve we got from the Spitzer Space Telescope. So the idea would be, the idea really is we want to detect light from this object, from this transiting object. So if we can detect any light from this transiting object, then combined with the age of the total age of the system and everything, maybe we can infer back the mass of the system. However, you can see here, we basically find the transit depths are the same within the error bars. It's 56.65% in the optical. It's 56.3% in Spitzer wavelengths. So again, we didn't really detect any light, but still any light from this transiting object. But still, that allows us to put an upper limit. And we think the upper limit of this system is 14 Jupiter mass. So really, this transiting object can be anywhere between 1 Jupiter mass to 14 Jupiter mass. We can also calculate its equilibrium temperature, which is about 165 Kelvin or minus 162 Fahrenheit. So it's very cold. You probably do not want to live there. But anyway, so this is the only transiting planet we know around the white dwarf right now. That's still really cool. So the big question there really is, how did the planet get to its current location, right? So there are two ideas. One maybe it has been there the whole time. It did survive this whole process. I'll play this again. I showed earlier. Basically, when there the whole time means even when the star is on the main sequence, when this white dwarf was like the sun, the planet just had been there. It just somehow magically survived this whole process. It's a possibility, but it's a very, I'll say it's a pretty long journey. Just want to show this solar system to scale again. The planet's orbit around this white dwarf is within the orbit of Mercury. So it's super close to the white dwarf. Can it really survive this whole process? This is what we are trying to figure out. And the second possibility really is it moved there recently. Recently means within the last 5 billion years, because this white dwarf's age is about 5 billion years. So maybe the planet only migrated there after the star became a white dwarf. I think it seems more likely, like because after the star had become a white dwarf, then maybe a kick from another planet or a passing by star would move this planet to its current location. And another thing I just want to point out is in this system, we did not find any debris disks. We did not find any rocky material floating in the atmosphere. So somehow this planet managed to arrive its current location intact. Okay, I see another question from Jamaica.
Yes, yes. Just a follow-up from myself, and then I do see that we have another question in the chat. But my question was that you mentioned just a few minutes earlier as you were introducing this slide, stars on the main sequence. Could you just briefly give us just a description of what does it mean to have a star be on the main sequence and the difference between that and the later stages of a star's life?
Sure. Okay. So main sequence is where stars spend most of their life on. Should have introduced that in the very early stage when I say life cycle of the star. So our sun is currently on the main sequence. And our sun is about a middle-aged main sequence star because it's about halfway through its lifetime. So main sequence really is where a star spends most of its life on. That's what we call the main sequence.
Oh, that's perfect. Perfect explanation. Thank you. And so then if I can follow up with our question. So our question is from Liz Flemings. And Liz Flemings asks, how is your data used to increase the our understanding of the solar system?
Right, I'll get there. Great question about how about our understanding about solar system. I'll get there, like in 2 slides. Yeah.
All right, awesome. All right. Okay, so we'll put you on hold for just a moment, Liz.
Heading there, yeah.
All right, there. Yeah. Go ahead.
Sure. All right, just a little bit more about this system. What we can do next, and is we really want to characterize its atmosphere, and we can use a technique called transmission spectroscopy. So basically, the idea is depend on the composition of its atmosphere. If you observe this feature at different wavelengths, it's just a little animation. If you observe it at 1.8, 2.1, 2.3 microns, you will see the transit feature, the transit depths would be different. I'll show that again. And with that, you can actually have a way to characterize the atmosphere of this planet, because this is one of the coolest planets we've ever seen, and because it also transits. So it's a great target for this. So we got time on Gemini with GMOS to characterize its atmosphere in the optical, and it will also be a really interesting target for the James Webb Space Telescope, which will launch next year. All right, with that, let me put my summary slide, the solar system in 6 billion years. So to start with, as I said, the sun will become a white dwarf, like most of stars in our galaxy. I've shown you that there are evidence for planetary systems around white dwarfs. I specifically discussing 2 systems. First is 1145. It shows evidence for a disintegrating asteroid. And for WD 1856, it appears to have an intact planet. And then come back to our question. So what exactly will happen to the solar system in 6 billion years, right? Honest answer, I don't know. The best answer I can tell you is I think there will be planets and there will still be asteroids around the sun when the sun becomes a white dwarf. And then you might wonder, what about Earth, right? What would happen to Earth? my personal view, I don't think Earth will survive. Sorry, because Earth is just too small, just too close to the sun. I think it will be tough. But don't worry, we have 6 million years to figure that out. Oh, sorry, 6 billion years to figure that out. So we have enough time. With that, I just want to say thank you for your attention, and I'm happy to take any more questions.
Thank you so much. Let's see, in the chat, we do have a few more questions. Okay, so first we have our Liz Fleming says, thank you for responding to her question. Sorry that we jumped the gun with that question there. And she is, yes, hailing from Memphis, Tennessee. All right, so we have Leonardo Paredes in the chat, and Leonardo says, with the white dwarf being much harder than a main sequence star, I would have thought that a planet orbiting would have had a much higher equilibrium temperature. Siyi.
Yes. Okay. Yeah, that's a very good question. Indeed, white dwarfs are much hotter than the sun. However, white dwarf is also much smaller. It only has the size of the Earth. So if you do the total luminosity of the white dwarf, it's actually only 10 to the -4 times the solar luminosity. So that's why the equilibrium temperature is actually pretty low, like for this system. Yeah.
Okay, and so Leonardo continues and says, is this expected, or are some planet properties just still need to be constrained?
And so the question is, I guess, how good can we constrain the equilibrium temperature?
Yes.
In general, it's pretty straightforward because it basically depends on, just as you said, the temperature of the star and the distance between the star and the planet, right? So all these properties are pretty well characterized. Then you can calculate the equilibrium temperature. However, the hard part is the planet really in equilibrium? It might not be in equilibrium. If it's not in equilibrium, then there will be a harder question. Yeah.
Yes, yes, absolutely. And you answered it well. I appreciate that. Let's see, in the chat, I just put out the final call for questions and comments for you. And let me just say, we have lots of clapping hands in the YouTube chat. I know you can't see it, so I'm demonstrating the clapping hands for you. And we also, in the chat, just so you know, in case you want to speak on this really quickly in our last few minutes, I did just drop the link in the YouTube chat to your paper and to NOIRLab, link to your press release. Could you maybe talk about the press release on the NOIRLab website that has a fantastic image done by one of our graphic designers, Joy Pollard? Tell us a little bit about this press release and your work here.
Sure. So the press release is actually about the second system I've discussed in the presentation. It's about that an intact planet transiting around a white dwarf. To me, this is really exciting, is just because we've been speculating there must be planets around white dwarfs all this time. I remember I would go to conferences and I would tell people, look, we find a disk. But then they will be like, where's the planet? You haven't found a planet yet. They basically wouldn't believe this result. Now I'm very proud, like finally, now we can show them, hey, we find one planet. I mean, we need more, but we find one, and that's a great starting point. So yeah, so the press release is basically about this discovery, and then about how we use different techniques trying to figure out, like, we think this object is really a planet. And so, yeah.
Thank you. And so for everyone in our YouTube chat, yes, please check out Siyi's paper. The link is there. Also, the link to our press release and to an amazing graphic that you can download, a kind of a cartoon explanation of what's going on in this and what's actually happening in the research and shown in the press release. And we have one more question from, it looks like Genevieve Running Wind. And Genevieve asks, will any of the planets in our solar system survive? I assume survive the white giant phase of our sun and all of that. Yeah. What can you tell us?
I know. So let me start by saying, it's very hard to predict just for one system, right? So like just start out there. So we can study a lot of white dwarfs and know statistically speaking what's going to happen. But what exactly happened to the system, solar system? The best way is to wait 6 billion years, unfortunately. If you're not that patient, just like I am, let me tell you. So from my personal view, it's more like my belief, not choose. I think the Jupiter will be fine. The Jupiter is big enough, it's further away enough from the sun. I think Jupiter or the gas giant, ice giant, they will be fine. Like they will be there. Jupiter might lose some of its atmosphere during the red giant stage, but I think most of it will be fine. But I think like Mercury, Venus, I don't think so. And Earth, really, I think Earth is on the edge. Like depending on exactly the mass loss process and what happens, like Earth might or might not make it. That's my guess.
Well, so if you use the two examples of the white dwarfs that you did talk about as possible outcomes for our own sun when it becomes a white dwarf, then in one case we see this disintegrating asteroid, which, correct me if I'm wrong, especially after showing the graph of the metal contents of both this asteroid and the Earth side by side, it's kind of possible that that asteroid at one point could have been a terrestrial planet, that maybe parts of it got blown off in the explosion of the star transitioning to white dwarf phase. And so that's sort of like one possibility. And then the other one would be almost no trace of terrestrial planets, just Jupiter has survived. And I've certainly learned in other talks that our planets are slowly making their way inwards towards the sun, right? And so this happens in other solar systems as well. So it's like Jupiter could eventually make its way closer to the sun becomes a white dwarf, and only the sun and Jupiter are left to dance together forever until the coldness of our universe.
Great summary, Alyssa. Yes, that's definitely one possibility.
Okay, so we have about 2 minutes left. So I think for studying white dwarfs and to bring more of like an idea of how astronomy applies to our lives here on Earth and in our solar system. So I think in studying white dwarfs, one reason would be to sort of inform maybe our future generations 6 billion years from now what to expect. But what other things do you think are like really exciting to learn from white dwarfs?
To me personally, I just think they are just interesting objects. Really, it's just to fulfill my own curiosity. It's almost in an interesting way. To me, astronomy is just something, it's just to fulfill your own curiosity, right? There's so many cool things out there. I remember when we first saw the light curve of 1145, the one with the disintegrating asteroid, we have no idea what's going on. We're like, did we make a mistake somewhere? Like, I really like this problem solving aspect of it, and then try to make sense of what's going on. Maybe it's more like personal fulfillment side. Yeah. Well, I guess another part really is the technology side, right? So we can build bigger, better telescopes, better instruments, and that really drives a big part of the discovery too. One part really is to using better instrument technology to study the system.
Yeah, for example, our adaptive optics system, which we featured in our science highlight, adaptive optics and the laser systems that were developed for telescopes to use this are actually now used in a lot of fields of biology as well, especially to look at very small things like neurons in a brain or parts of a fish. I believe there was some research in looking at a zebrafish with a laser.
Cool.
Okay, well, that's all of our time. Do we have any last questions in the chat, Jamika?
Let me take a look. We have a few more comments from Genevieve. Genevieve says, I love that, Alyssa. So in reference to a comment you made a little bit earlier. And then we also have a comment from another one of our Gemini NOIRLab colleagues. It says, Jen Miller. She has lots of clappy hands for you, Alyssa and Siyi. So we appreciate everyone. in the chat for joining us. And also we have, more applause is coming in for you. This is from Leonardo Paredes. He says, great talk, Siyi, thank you. Also applause from Leanne. So fabulous talk, very informative. And for all of you in the YouTube audience, please definitely check out Siyi's paper. The links are there in the chat. We will also have the link underneath the video description when the recording is published, hopefully tomorrow. Thank you all so much. Back to you, Alyssa.
All right, yes, thank you everyone for tuning in. Thank you to Jamika for moderating and to Siyi for speaking with us today. If you have any final remarks, please feel free. And we'll see you again next week for another Live from NOIRLab.